Okie dokie artichokes. In the last video, we covered an introduction to the derivatives of trig functions. And that went over fairly well, right? It's just 6 things we need to memorize. And I gave you a hint that really if you just focus on knowing 3 of them, the other 3 are pretty easy, right? Take the derivative of anything with a co in front of it, out pops a negative sign, and there's some relationship between all of them. And so now we're going to take a pause. I know I mentioned that I was going to hop into the derivatives of exponential functions and logarithmic functions, and we still have to make our way to inverse trig functions as well. But I'm going to take a sidebar and talk about this concept called implicit differentiation, which is basically just the chain rule in disguise. Okay, the chain rule in disguise. And here's what I mean. So, we know if I were to give you something of the form that's like y is equal to sine of x, okay? Now, just bear with me for a second. If I were to take the derivative of both sides, so I apply the derivative operator to both sides, so I'm going to do this, I'm going to take the derivative with respect to x of both sides, right? So I have my derivative, ddx of y on the left side, ddx of sine of x on the right side. On the left side, the derivative of y with respect to x, we can't do anything with it, right? Y is a function, I can't touch it, so we simply just write the notation dy dx. And maybe as a sidebar before I continue, people always, ask this question. They say, how come, if I were to take the derivative of sine of x, right? Sine of x becomes cosine of x, right? It completely changes when I take the derivative. But if I take y and I take the derivative of y, how come it just becomes this dy dx, right? Why do we even have this notation in the first place? And the idea is that y, right, the variable y is some function. It's some function of x, right? So if you were, if I just give you this random letter y and I say take the derivative of this with respect to x, the derivative of y, if I do this and I say take this derivative, the derivative of y is going to change depending on what y is. If y is the sine function, then this thing becomes cosine of x. If y is equal to x squared, then this is 2x. Right? If y is equal to x cubed, then this is 3x squared, right? So depending on what y is, our derivatives would all be different. And so instead of being able to actually get a concrete answer here, right, we can't do that. We're just being given this letter y. And so this is the reason that we describe the derivative of just the variable y all by itself. We just say, okay, that thing is dy dx. We're going to call this the derivative of y with respect to x, the change in y with respect to x. And then depending on what's on the right side of this equal sign, that's when we get, dy dx equals blah. So that's the reason for why this notation exists. And it's a very important idea that we need to have down, right? The reason why we write dy dx in the first place before we kind of continue on. Okay, so back to this example. So derivative of the left side, we just get dy dx. We can't really mess around with it. But on the right side, we're going to get cosine of x. And now I'm going to do something a little bit silly maybe, right? Remember that when we learned about the chain rule, I said that the chain rule is without a doubt the most important derivative rule that exists. And it exists in everything, right? Because if I wanted to, I could identify that this is like my outside function and this little x on right there is my inside function. And I could, in theory, say that the chain rule is taking place, right? The derivative of sine of something, right? The derivative of sine of something just becomes cosine of that something. And so, which is, by the way, what we got. And then we do the derivative of the inside, which in this case, the derivative of x with respect to x is just 1. And so we don't ever write really this part, right? We don't really think about using the chain rule, but I want to stress something, which is that the chain rule always exists. It's always in effect. Okay, now a lot of the times it just ends up being multiplied by 1, but you could think about doing it if you so chose. Now the reason that I'm bringing this up is because I'm going to give us a brand new problem. And the problem that I'm going to give to us here is, let's see here. Let's do xy plus x squared is equal to 4x, okay? And I would like us, without separating anything, I would like us to take the derivative of this equation, okay? So without, needing to separate anything, right, I could, just as a heads up, I could write this as xy is equal to 4x minus x squared. I can move that x squared over, and then I could divide out by x, right? Y is equal to 4x minus x squared over x, and I could cancel things and take the derivative here. I'm going to say, just for the sake of practice right now, let's take the derivative of this thing right here, okay? Let's try this out. And let's just do it at this particular step. So we're going to have the derivative of xy plus x squared is equal to 4x. Okay, oops, actually, maybe I'll separate these. So took the derivative of the left side equal to the derivative of what we have on the right side. Okay, now on the right side, it's fairly easy, and even on the left side, it's mostly easy, right? The right side, we're just going to get 4. And the left side, the derivative operator is linear, so I'm going to take the derivative of x times y, and the derivative of x squared, well, the derivative of x squared is just 2x, so we really only have to deal with doing the derivative of x multiplied by y, and this is going to be the interesting part for us, which is that is x multiplied by some function y. I don't know what y is, but it's some function, and so that to me screams product rule. So I'm going to label this first x f, I'm going to label the second one g, and then we are going to just do the product rule. So I know for the product rule, I need f prime, right? And f prime here is just going to equal 1, right? The derivative of x with respect to x is just 1. And I'm going to need g prime. Well, last time I checked, the derivative of y with respect to x is going to be dy dx. Okay, that's it. Or if you wanted, you could write and say it's y prime. But the point is that now I can use the product rule and just say, okay, well, the product rule says that it's going to be f, which is my x, times g prime, which is going to be my dy dx, plus f prime, which is just 1, multiplied by g, which is my y function. So there's what y is, okay? And so then I'm going to have left over my plus 2x is equal to 4-bit that we had from earlier. And if the goal of this problem is to solve for the derivative, right, it's to get dy dx by itself, well, now at this point, we're practically done. I can just say, okay, I have x y prime plus y plus 2x is equal to 4, right? This is my equation. I'm going to put everything on the right side that doesn't have a y prime attached to it. So we're going to get xy prime is equal to 4 minus 2x minus y. And last but not least, I'm going to get 4 minus 2x minus y over x. And this is my answer. Now, one thing that's weird about this whole thing, right, besides the whole process of doing the derivative of y and saying the derivative is dy dx, the thing that's a little bit different about this one compared to the other problems we've done is that this derivative has y in it, right? The derivative is here. Normally we just have x's, but we inherently have a y in it, which is kind of a little interesting. Like the derivative of y, right? The derivative of y depends on the original function value of y. And that is where we kind of get the name implicit differentiation. So we say that a derivative is explicit. So an explicit derivative would be one that where we get like y prime is equal to 2x. Okay, that's explicit. There's only input variables here, right? It doesn't depend on y. It's just, all depends on x. Great. But an implicit derivative is one where the derivative is written in such a way that y is part of the derivative. Now, how do we interpret this? Okay, now let me do one more example, and then I'll be like, all right, let's try and make some sense of this intuitively. So really quick, as an example, let's say that I have, if we're talking about the derivative as being slope, right, the slope of some function, I'm going to give you our old friend, the unit circle, x squared plus y squared is equal to 1. Right, and I'll even put in a cute little drawing of our friend the unit circle because I miss it so much. Right, there it is, the unit blob. Oh, there we go. Right, there's our old friend the unit circle. Okay, and remember that the derivative, if at the end of this I get dy dx is equal to something, the derivative will tell me, you give me a point on this circle, and I can tell you how steep it is at that exact point, right? That's the idea. That is the purpose right now of solving for the derivative when it comes to trying to, sketch a graph of something, all right? And so we're going to do the derivative of this equation. And you might notice, right, I can't really easily write it in the form y is equal to stuff, right? Because when we do that, if I were to try that, I'd get y squared is equal to 1 minus x squared. And then I would have y is equal, right? If I take the square root of both sides, I get a plus or minus square root 1 minus x squared. And now you've got to take the derivative of two functions with the square root. All of a sudden, this thing just got super duper hairy, right? And so instead of doing that, we're just going to take the derivative right at the very beginning and just try and find a dy dx somewhere. So what I mean is we're going to take the derivative of both sides, just like we've been doing. So there's x squared plus y squared equals the derivative of 1. Well, lucky for us, the derivative of any constant is just 0, right? So that's nice. And on the left side, I'm going to get, all right, so in this guy here, the derivative of this is just 2x. And the reason it's just 2x is because you could think about it as the chain rule existing, right? We could have said, I've done this example in the chain rule video, actually. We could, treat this thing as the outer function is like the squared bit, and the inside function would be the x part. And so, we say the derivative of the outside would be 2 times whatever's there, in this case, x, and then multiplied by the derivative of the inside, but the derivative of the inside here is just 1, so that's why the derivative of x squared is just 2x. Okay, so you're like, all right, why are you telling us this? I know how to take easy derivatives. Well, it's because we're going to now take the derivative of the second piece. And the derivative of y squared, we want to think about it like needing the chain rule, right? We have an inside function, and we also have an outside function. So the derivative of the outside function, right, the derivative of something squared is just going to be 2 times that thing raised to the first power. In this case, that thing is y. But then we have to do the chain rule, right? Then we have to multiply by the derivative of what's on the inside. Well, the derivative of y is just y prime. So, or in our case, I'll write it as dy dx, right? So this dy dx pops out, right? And then all of that equals 0. And the goal of this problem is to simply solve for dy dx. So at this point, we're going to move this 2x over to the other side. I'll have 2y times dy dx. Remember, this is a first power, not a prime, so don't get confused, equals negative 2x. And then last but not least, I can get dy dx all by itself by dividing the 2y on both sides, which is just going to leave us with a negative x over y. And there we have it, right? This is the derivative of the unit circle equation. And again, you might notice a little bit, different than normal. We have a y sitting in our derivative. And so this is what we call an implicit derivative, right? This is an implicitly defined derivative. And I'm just writing this down so that you know, right, when you read the textbook or you hear it in a video, you understand what we're talking about. Just that the derivative, right, is going to have a y sitting inside of it. And you're like, okay, well, how do I use this, right? Well, The idea is that if I were to give you a point on the unit circle, like let's say I give you the top point up here, which is the point 0, 1, well, I can plug in that point into this equation, and I could say, okay, so the derivative evaluated at the point 0, 1 is going to equal negative 0 over 1, because 0 is x and 1 is y, and that's just 0, which should make sense because we would expect that the slope is flat right at the top of that unit circle, right? And we could do this for any point. I could evaluate it for, another point on the unit circle is going to be root 3 over 2, comma 1/2. That's a point on the unit circle. And so I could say, okay, so we could calculate the slope at the point root 3 over 2, comma 1/2, no problem, because that's going to be negative. So the x value is the root 3 over 2. The y value is the 1/2. And when you do this, when you do the division, right, so we need to remember how to divide by a fraction. So dividing by a fraction is the same thing as multiplying by the reciprocal. So we have negative square root 3 over 2 multiplied by 2 over 1. And this is just going to equal, those 2's will cancel, negative square root 3. And so this tells us that the slope here is going down at a rate of negative square root 3, which means that for every 1 unit that I'm going to the right, I'm going to drop down a minus square root 3 units. Right? That's the steepness at that point on the unit circle. And this is implicit differentiation. So we can do it, right? We can make it as crazy as we want, and maybe I'll do one more quick example. So for example, let's say that we're given, let's say given sine of y cubed is equal to x, or let's do 10x to the 6 plus 4x, right? So find dy dx. Okay, our input variable x, our output variable y, find dy dx. Again, there's not really a very easy way to get y all by itself and to write this equation as y is equal to stuff. And so we're just going to, right off the rip, we're just going to take the derivative of both sides. We're going to apply the derivative operator to both sides of this equation, and we're just going to do it. So I'm going to start with the right-hand side. So the right-hand side, we're going to bring down that 6, and we're going to get a 60x to the 5th, and then we're going to have a plus 4. So the right-hand side taken care of, great. Now the left-hand side, we've got to be a little bit careful because we have like an outside function and an inside function of y cubed. And so let's take that derivative. So the derivative of sine is going to be cosine of stuff, right? And in this case, that stuff is y cubed. But then we have to multiply by the derivative of y cubed. So, off to the side, we're basically doing this. And we have to remember that the derivative of y cubed is also going to have the chain rule, right? Because, maybe a more appropriate way to write this would be to write it as y raised to the third power like that, right? The chain rule always exists. And so the derivative of y cubed is going to equal 3y squared, but that's just the derivative of that part I just highlighted in green, right? That's just the derivative of the outside part. And then we need to multiply it by the derivative of the inside function, which is dy dx, okay? And so we're going to end up having, so going back to what we're doing here, we're taking the derivative of sine of y cubed. So we got cosine of y cubed multiplied by 3y squared times dy dx, because that is the derivative of this inside bit. And again, our goal is to get the derivative all by itself. And luckily for us, everything's being multiplied on the left-hand side. So this tells us that dy dx is just going to equal the 60x to the 5th plus 4 divided by cosine of y cubed multiplied by 3y squared. And this is another implicitly defined derivative because the y is sitting right there in the equation, okay? Yeah, so I think that's going to do it. I think I did a few examples, kind of covered the idea of why this might show up and when this might be easier and things like that, right? Because not every function is just y equals something. We have functions that look like, just like the unit circle, x squared plus y squared equals 1, right? We don't just have y is equal to stuff. And so, yeah, so now with this tool under your belt, I think implicit differentiation is the one that kind of gives people the most amount of trouble, right, when they first learn it. But if you understand the idea of essentially that the chain rule is always taking place, it's just the chain rule, it's nothing you don't already know, and that the chain rule always is taking place, then you're going to be good to go, and implicit differentiation won't be too bad. Now that you have this under your belt, we can get back into learning some of the other derivatives. As promised, up next will be logarithms, exponential functions, and of course, inverse trig derivatives.